And we saw the definition, or our first look at a definition of continuity for functions. Okay, and this definition says that the function f defined on the real numbers to the real numbers, that we're going to say it's continuous at the point A, so at a certain point in its domain. A is a point in the domain of X. So in the left-hand copy of R, if you like. We're going to say it's continuous at X equals A if the limiting value of the function as the argument X approaches this limiting value of the argument, the limiting value of the function there is actually equal to the value that the function takes at f of A itself. Okay. We looked at some examples or some illustrations of continuous behavior and non-continuous behavior, and in particular we considered this kind of nasty function, well, this function sine of 1 over x, which has got a kind of nasty behavior close to x equals 0, because this function is oscillating up and down an infinite amount of times as you approach x equals 0. So this function has, if you like, some kind of a fundamental discontinuity, discontinuous behavior at x equals 0. I mean, it's not even defined at x equals 0 as it stands, just with that expression sine of 1 over x. There's no meaning we can give to that at x equals 0. But even if we separately supply a value or assign a value to the function at x equals 0, that cannot be done in any way so as to make the function continuous at x equals 0. Okay. So having introduced that definition, then we now want to say a bit more about it and look at some of the properties of continuity. Okay. And what do we mean by properties of continuity here? Well, what we want to explore or find out about is how this property of continuity relates to the operations that we have on functions. Okay. So the kind of question is, how does continuity relate to the operations that we have on functions, the things we can do with functions? If we just assume our functions are from the real numbers to the real numbers, they can be on reduced domains or codomains as well. But just for the moment, just think of them as functions from all of the real numbers to all of the real numbers. Well, if you've got functions like that, there are a number of natural operations you might do with them. You can add functions together. You take two functions, you can add them together. You can multiply them together. You can form quotients of functions under certain circumstances, as long as the denominator function g is never going to take on the value 0, then the quotient of two functions will be well defined. Those are operations on real valued functions that we introduced in chapter 3. And then finally, a very important function is, or a very important operation is that of composition of functions. Or if you've got two functions from the real numbers to the real numbers, you can combine their effect by running one after the other. Okay? Remember, the definition of f after g applied to an argument x. This was f after g, meaning you apply g first to the argument x, then you apply f to the result. Okay? And the definition of adding two functions together is just adding their individual values. And f times g is defined in the usual way as well. And so on. Similar definition in the obvious way for the quotient of two functions. So what do we want to mean? What do we mean when we say we want to know how continuity relates to these operations? We want to know, or we want to be sure
that all these operations, and one way mathematicians tend to word it is we tend to say that they preserve continuity. And we'll have a look at precise statements in a moment. They're in the notes. But what we mean by preserving continuity, preserving this property of continuity, means that if the two ingredient functions, f and g, if they are both continuous at a certain point, then so will the new function that you form, either f plus g, f multiplied by g, f composed of g, etc., or f divided by g. Okay? So applying any of these operations to a pair of functions, that preserves the property of continuity. It won't destroy the continuous behavior of the two functions. So if you feed continuous functions into these operations, the objects you get out are also continuous. So that's very nice to know, okay? That means that all we have to do, as long as we're sure that our basic kind of atomic functions, if you like, are continuous, then we know that whatever complex or compound functions we assemble out of those ingredients using these operations, that those functions will also be continuous as well. Okay? Now, this is a very natural thing in pure mathematics, and this kind of structural pure mathematics is, identifying natural properties that these objects have and natural operations, and always being interested in whether the property is preserved by the operation. When you apply some kind of process to something, is a certain property that it has initially, is that preserved? Does it still have the property at the end of the transformation? Transformations we're talking about here are operating on these functions to produce new functions. Okay, so let's just look in the notes there. These properties are stated here in theorems 4.3 and 4.4. Where are they? There they are. So the first one deals, or just packages up the sums, products, and quotients. 4.4 deals with composition, but they're all saying effectively the same thing. Okay, so this is basically just what I've been saying. Theorem 4.3, suppose f and g are both continuous at a point x equals a. We want to be sure that the linear combination of the two functions, alpha f plus beta g, is also continuous at that point. We want to know that the product function f times g is also continuous at x equals a. And we want to know that the quotient function f over g is also continuous at x equals a. And a very similar thing for composition. If f and g are both continuous, so okay, so here the continuity has to be in two different places. So as it's stated there, we're asking for f to be continuous at a point A and g to be continuous at the point f of A. Then when you combine them in a composition like g after f, and it's written the opposite way around, which how it's written there. Which one goes first? If the original function f is continuous at this point A, g is continuous at the image of A under f, then the composition function g after f will be a continuous function at that original argument A. So these are nice structural properties that relate the operations we can do with functions with this property of continuity. But at the moment, the definition we have is just this, maybe one which is slightly informal or slightly vague on the details. Just saying that the limiting value as x approaches a of f of x is equal to f of a. Just like when we were studying sequences and series, we need to put a bit of flesh on the bones of that vague definition. Okay? So we need a formal definition of continuity. Let's say, to prove these, we need a precise technical definition of continuity. Again, technical definition of continuity that exposes all the details, and that will allow us to argue mathematically about it. We need a precise technical definition of continuity that will allow us to construct rigorous arguments. Now this formal definition of continuity we're about to encounter, it reminds us a lot of the formal definition of convergence for sequences. It features this, your new favorite letter, epsilon, the Greek letter epsilon. So it's again a kind of epsilon type definition. So first of all, we'll recall the definition of convergence. Convergence for sequences. I think it's good to glance back at that again, because as many of the ideas or ways of thinking about that definition also apply to this new definition you're about to see. So there we said that a sequence AN converged to A. What that meant, this was if and only if, for every epsilon greater than 0, there existed some point n, such that n bigger than or equal to n, it said that the sequence elements were within a distance epsilon of the limit point A. For all epsilon there exists an n, which for every index little n past that capital N, the distance between an and minus a was less than epsilon. Okay. That was our formal technical definition of convergence. You all remember from last term. Okay. Okay, so the formal definition of continuity looks like this. Shares some features with this. Okay, but it's in a different context. Before we were talking about a sequence of elements, just a plain old list of elements, A1, A2, A3, A4. So is that okay? Is there anything you can't decipher? Do shout out if anything's unclear there. Now we need to understand this formal definition of continuity quite well. I think the best thing to do is just to dive in, jump in feet first into it, and just stick it down on the page, and then we'll try and decode the definition and understand the various elements of the definition. Okay. So the definition says, and it's printed in the notes, but you should get used to writing it. F is continuous. O-U-O-S. No, that's fine. You have to learn how to spell continuous as well. You don't know it by now. U-O-U-S is continuous at x equals a if and only if. Okay, so here it is. For every epsilon greater than 0, there exists a delta greater than 0. And this has the property that if x minus a is less than delta, this implies that the absolute value of f of x minus f of a is less than epsilon. Okay, certainly recognize something. Before we had absolute value of an minus a less than epsilon. Now we've got absolute value of f of x minus f of a less than epsilon. Okay, that looks kind of similar. It's like a similar thing going on. We no longer have the exists an n. That kind of role has been replaced by this delta. Okay. So certainly on the surface level, you can certainly see some similarities with the previous definition.
Is that the n at the beginning of the definition?
There.
Not at the top line. At the start line.
That's IFF. That's
She means where it says x equals a before.
that's just F.
N.
No,
Oh, it says is.
that's
F is.
F is. Yeah, excuse me. Sorry. And yeah, and the script is F is. Now, just as how we illustrated the definition of even illustrated of it. page. I'm just going to repeat that diagram on the page, but I just want to talk about it as we construct it. So here's our function f, the x-axis, the f of x-axis. Here's our point A. Now remember, there's our point A. Somewhere over here is the point f of A. Our original informal definition of continuity said that the limiting value as x approaches A. So x approaches A down here on this axis. Okay. As x approaches A, the limiting value that the function takes, you track the values of f of x as x gets close to A. Well, if you're coming from this side, the value will be creeping up and up and up, up and up and up, and it's going to converge to or get closer and closer to the value of f of A. Okay? But there's two processes going on there. The x is getting close to A down here, and hopefully our f of x is getting close to f of A up there. Okay? So there's two kind of processes of getting closer to going on. Okay? And so these are described, or the parameters describing this degrees of closeness are the epsilon and the delta. The epsilon is living up here. So the epsilon defines a radius around the value f of A up here. So you've got f of A minus epsilon down here, f of A plus epsilon up there. The definition says no matter what size of radius there around f of A, so that's interpretation of this for all epsilon greater than 0. So no matter what size of radius you care to specify around f of A, there will always exist a delta. Now what's delta is giving an upper bound to the distance between x and A. So delta, A plus delta, A minus delta. Delta is a radius, if you like, around the value A in the domain of the function. I should have drew those a bit haphazardly. I hope they work out. Yeah, I'm lucky. They're just about 2. So the way I've drawn my delta there, you'll notice that if you look at the range of possible values you can get, I was lucky that this lives inside here. So that kind of wibbly-wobbly green region I've drawn there on the vertical axis, that is indicating the possible range of values for the function f you can see if you give it an argument x somewhere within this interval here. Okay. And what's nice is that range of f values fits within the epsilon radius around f of A. Okay. And if that can always be done for any choice of epsilon, for every choice of epsilon, if a valid delta can be found, that makes this implication true. The implication is if x is within a distance delta of A, so if x is within this interval here, then the corresponding function values, f of x and f of A, will be within a distance epsilon of each other. Okay? That certainly works out with how I've drawn it there. Okay? If that can be done for every epsilon, then the function is deemed to be continuous at x equals A. So this reminds us a lot about the definition of convergence with sequences. Certainly. And similar thing, if the epsilon is made smaller, that interval around f of A is shrunk, it's probably going to require a smaller delta as well. Yeah? So if you're asking for a high, a better degree of closeness between f of x and f of A, you probably need a better degree of closeness between x and A. Okay? If you want f of x to be close to f of A, you're probably going to want x close to A. But this can always be done. So when I say if this can be done, this means if the delta can be found, if the delta exists, for every value of epsilon, if there does exist a delta that makes this implication work, then the function is called continuous. So this is our formal definition of continuity, and it exposes all the processes that are going on. X is getting close to A, that's governed by delta. F of X is getting close to F of A, that's governed by epsilon. So it exposes all the technical details that is going on. And so we've got full view of everything there. So that definition should allow us to prove those properties of continuity we're interested in proving. Okay? And we'll go ahead and see an application of this, see a good application of this definition now into proving one of those properties. Now this is a definition you all need to become familiar with. It looks strange at the start. It's slightly more complicated, perhaps. Well, it's not really. I don't know. I think people tend to find it a little bit more complicated than the definition of convergence for sequences, but there's a lot of similarities between them. Okay. Okay. Any questions at the moment, or queries, or things you'd like to clarify about it? Okay, the point of the definition, the power of it, is that it allows you to provide proofs of those properties, okay? Just sitting there as a definition on the page and declaring that that's the definition of this property of continuity, okay, that's okay, but that's to really appreciate the power of it and the meaning of it, you have to see it being used to prove things about the property. And a good, detailed definition of a concept, one way of thinking about it, is one that allows you to do work with that definition, to use it to construct rigorous mathematical arguments for the properties. Okay, so let's have a go at proving perhaps the most approachable one of these, which is the linear combinations case. Okay, so we'll take the theorem 4.3. The linear combinations part. So first be clear on what we're assuming. We're assuming that the functions f and g are continuous at a certain point. Okay? So we assume, so we let f and g be two functions continuous at A. Conclusion we're trying to reach, proof we're trying to achieve, is we want to we will prove, let's get them side by side here, that alpha f plus beta g is also continuous at x equals a. Okay, we better not leave anything unsaid. So alpha and beta are just two real coefficients. They're the coefficients of the linear combination. They can be anything. So we want to start from the assumption, use that and the definition of continuity to prove our required conclusion. Okay? Now, before you embark on these arguments, the first thing to do is to be very clear on what you're assuming and what you're trying to prove. Okay? And label them as such, just to be clear where you're starting and where you're trying to get to. And I think the best way of explaining how this proof works and for how to learn it and to how to kind of rediscover it each time when you come to try and produce it again or exhibit it, whether that be an exam or to prove it to another person and so on, is to think firstly about, well, if this is the conclusion I'm trying to get to, what exactly how exactly do you arrive at that conclusion? Meaning, well, this speaks about this term continuous here. Well, we've just gone to the trouble of giving a formal definition to continuity. So what I like to do first is to unravel the conclusion one step backwards, so to speak, and put down very clearly what we have to arrive at. Okay? So we need to show that for every value of epsilon, there exists a delta such that x minus a less than delta, that implies, so really all I'm doing here is I'm really just rewriting the definition, but instead of quoting f in both positions, I'm quoting the function I'm interested in. Alpha f plus beta g of x minus alpha f plus beta g at a, just left myself enough room, that should be less than epsilon. Okay. We want to prove the thing is continuous. To prove it's continuous, we have to satisfy the definition of the continuity. Okay. So the kind of key thing where it turns is in this existence here. So whatever value of epsilon is offered up by somebody, we have to show how to find the delta that makes this implication work, or how to find a delta that makes that implication work. Now, one thing we can work on and explain here, so if we want to make this implication work, we have to show how to make this inequality on the right true. We have to show how to make this absolute value here less than epsilon. So one thing we can do is examine this absolute value and see how we're going to get a hold on that. Now, you can see that it involves f and g, and we're assuming that f and g are continuous. And assuming that f and g are continuous means you're assuming something about absolute values of f of x and f of a, and g of x and g of a. We're assuming that we can make those small. Okay, because the fact that f is continuous means that we can make this absolute value small. The fact that g is continuous means you can make the absolute value of g of x minus g of a small. And f and g are the ingredients here. But at the moment, they're kind of parceled up together and tracked together. So to be able to exploit the assumption, which says that f is continuous and g is continuous, we have to kind of see those absolute values of f and absolute values of g. We have to see those appearing on their own. At the moment, it's all the f and g are muddled up together. So we want to kind of separate them out. And when we do that, we'll start to see a way to construct a proof. Okay? So I'm going to continue examination here. Notice that, and I'll take this absolute value here, alpha f plus beta g at x minus alpha f plus beta g at a. Well, I'll just do some straightforward manipulation at the moment to gather up all the f's together and gather up all the g's together. Okay? At the moment, they're all mixed up. I want to separate them out. And separate out the alpha as much as I can and separate out the beta as much as I can. Well, using properties of just the definition of what these additions and subtraction mean here, I can write this as alpha times f of x minus f of a plus beta times g of x minus g of a. Okay. Just apply, so what I've done there is I've just applied the definition of what this addition of these two functions means, and I've factored out the alpha from the f's and factored out the beta from the g's. Okay, that's good progress. That kind of simplifies it a bit, because at least now we can see something to do with f over here, and separately something to do with g. Now remember, the definition of continuity speaks about the absolute value of f of x minus f of a and the absolute value of g of x minus g of a. I'm nearly seeing that here. I see f of x minus f of a. I see g of x minus g of a. But what I want to see is I want to see them with absolute value signs around. Now I do here, but there's one set of absolute value signs on the outside, and it's all some kind of mixture of it on the inside. But I literally want to see, that exactly on its own, and the version with G there on its own, with separate absolute value signs around. And the way to see that happening is to exploit this property of absolute value that we encountered last term, which is the triangle inequality. So what we've got here is an absolute value of a sum, and the triangle inequality for absolute value says that that is always less than or equal to the absolute value of the first thing plus the absolute value of the second. I'm going to do another thing simultaneously. I'm going to take these, separate out these coefficients alpha and beta. Now I don't know whether those alpha and beta, whether they're positive or negative. All I know is they're real numbers. They might be negative, they might be positive. So when I factor those out, I have to factor out the absolute value of alpha times the absolute value of f of x minus f of a. And this is added on to the absolute value of beta multiplied by the absolute value of g of x minus g of a. So you can see what I'm teasing out here. This large absolute value, which in order to achieve my conclusion, I have to show that can be made less than epsilon. So I'm interrogating it here, I'm examining it here. I've been able to show that it's less than alpha times, or absolute value of alpha times this, plus the absolute value of beta times that. Okay. But now I see f of x minus f of a on its own, g of x minus g of a in its own. And I've assumed, look up here, reminding me here, I've assumed that f is continuous, so I can make that arbitrarily small. That's the definition of continuity. I can make that arbitrarily small. Similarly, I've assumed g is continuous at a, so that can be made small. Okay. So how small should I make f of x minus f of a? How small should I make g of x minus g of a in order so that the whole thing is less than epsilon? Well, basically, whatever epsilon is, if I can make this stuff here less than half of epsilon, and this stuff here less than half of epsilon, then when you add them together, it'll be less than epsilon. So the fact it's come out as two terms means I should aim to make this term less than half of epsilon and this term less than half of epsilon. But now we have to take account that both of them are also multiplied by these other fixed terms, absolute value of alpha and beta. Okay. So here we can go now, and we can start building up to our construction of the delta. Okay. So we start off by saying, so this is some preliminary investigations. Notice that this. Okay. I'll just put in a note here, triangle inequality, just to remind myself that that's what I was using. The reader. So now we need to let epsilon be greater than 0. Remember, the way the definition works is for every value of epsilon, there has to exist a delta. So I'll just consider a general positive epsilon, and I now have to show how to find the delta. But you see, I know that I can make absolute value of f of x minus f of a. I know that I can make that small. I can make that as small as I want because f is continuous at a. And I'm going to make it smaller than, basically the idea is half of epsilon, but because it's multiplied by absolute value of alpha there, I need to include that in the denominator as well. I know there exists a delta, I'm going to call it delta 1, such that if x minus a is less than delta 1, that's going to imply that that is smaller. Similarly, now that choice might, hopefully you can appreciate why I put the absolute value of alpha in the denominator position there. You'll see it all click together shortly. Also, there exists a delta 2, and this is talking about g, such that if x minus a is less than delta 2, that implies the absolute value of g of x minus g of a is less than epsilon over 2 times the absolute value of beta. Now, why am I justified in saying that those deltas exist? Okay? I'm justified in saying that because we've assumed, still on the screen, we've assumed, just up there, we've assumed that f and g are both continuous at x equals a. So that means no matter what the epsilon, we can find a corresponding delta to make the implication work. So the epsilons I'm using when I'm invoking the continuity of f and g, the epsilons are slightly different. I'm using epsilon divided by 2 times absolute value of alpha, and epsilon divided by 2 times absolute value of beta. So both delta 1 and delta 2 do exist, since f and g continuous at x equals a. Okay. So that's what justifies me bringing in the existence of delta 1 and delta 2. Okay. So now we can put them together. But you see, I want both of these. So you can see there when I say f of x minus f of a is less than that, g of x minus g of a is less than that, when I substitute those in, this right-hand side here will come to epsilon. Because the alphas will cancel, the betas will cancel, and you'll get epsilon over 2 plus epsilon over 2, so you'll have epsilon. Okay. But that means I need both of these inequalities here to be true, but they're both true at different times. This is true when x minus a is less than delta. This is true when x minus a is less than delta 2. So I have to be sure that both of these things are true simultaneously. And the way to do that is to now let my delta, and this is exactly the delta that I'm looking for up here. I'm going to underline it in red. So here's where I'm defining the delta. So this delta here is exactly that delta that's talked about up there. And I just choose it to be the smaller of delta 1 and delta 2. Sorry. Whichever one is the smallest. One of them is, maybe they're both the same value by fluke. But whichever one is the smallest, I just let that be the value of delta. So now you see so if x minus a is less than delta, then both star 1 and star 2 hold. Star 1 and star 2 are these two inequalities here. Yeah? The inequality involving f, the inequality involving g, star 1 and star 2, they are both holding, they are both true, those two inequalities, since x minus a is less than delta. Because if x minus a is less than delta, then it's less than delta 1, and it's less than delta 2, because delta is the smaller. That's the way you kind of combine these two conditions into one. And both hold, and we see that this object here that I want, the absolute value of alpha times alpha f plus beta g. You're off the screen again, sorry. Alpha f plus beta g evaluated at x minus alpha f plus beta g evaluated at a. This absolute value. So what I'm doing now is I'm going back to this investigation here. So I'm taking the top line of it. I'm going to skip the intermediate lines. I'm just going to say it's strictly less than absolute value of alpha times this, but this I know now is less than epsilon over 2 absolute value of alpha plus absolute value of beta times that. Okay, so this inequality, this strict inequality, comes from combining the above inequality up here, this one, and these two, star 1 and star 2. So this is from the above inequality, and star 1 and star 2. And of course, this thing on the right-hand side is just equal to plain old epsilon. The alphas cancel, the betas cancel. Epsilon over 2 plus epsilon over 2 is epsilon. So when you've done that, you kind of have to stand back from a bit. It's a bit like finishing a big painting or something. You stand back from it a bit, you admire it, and you just check that it is what it claims to be. It is a proof of this. We do some boxing in green. I can't quite get it all into the same. Or maybe I can. Might go higher. I need to snap. Sometimes I go higher. There we go. Okay. So the key point here is this was a general epsilon here. There is where we showed how to construct the delta. And the delta produced the required inequality. This thing here was less than epsilon. Just kind of highlighting,
Yeah.
highlighting the required inequality.
Yeah.
Okay. So the two things we set out at the start, the assumptions and the thing we were required to prove, you can see that's been achieved. I've used the assumptions in constructing these two implications here, the exists delta 1, the exists delta 2. I chose them well. I used the upper bounds I wanted to talk about well. I chose those well. I chose them in such a way that when I combine them down here, it would end up at epsilon. So no matter what the value of epsilon is, here's how to choose the delta that makes this inequality hold. Okay, if x minus a is less than delta, then this. Okay. So this proves that alpha f plus beta g is continuous. Continuous at a. Now, if you look back to how we proved the linear combinations part of the algebra of limits theorem for convergence of sequences, you'll see that the structure of the proof, the structure of the argument is very similar to that. It's really essentially exactly the same argument, but just adapted to fit into this new context. When you look back at the other argument, you'll see that at these two locations, we knew that there existed a capital N1 and a capital N2, and then we chose our new capital N as the maximum of N1 and N2. But very similar things going on here, just adapted to the new context. Okay. So that's only one little part of 4.3 and 4.4. We've still got products and quotients and composition to go. But I'm going to set as an additional exercise for you to do in the meantime, between now and next Wednesday, when we're going to discuss them, is look back at the convergence of sequences proofs, and use those in a very similar way, and so adapt those to construct. Say that again. All of that comes out as equal to epsilon when you multiply it out and add it together. Because the alphas cancel, the betas cancel, you get epsilon over 2 plus epsilon over 2. So look back at those other proofs for convergence of sequences, for products and quotients, and adapt those to construct proofs
But top one.
Oh.
The top one.
with the continuity of f times g and f over g. And that's something we'll look at next Wednesday, along with the similar result for compositions. Okay? Okay, we'll end it there this evening. Thanks for your attention. If you've got any individual questions, feel free to come up.